Okay, so I think we are live. Can you guys hear me? Is anyone there? Hey. Great. Great. Okay, good. Somebody's on. Great. So this is review for Math 122, exam number 2. Okay. Yep. Okay, good. So do you guys have any particular questions you want to start first? From the review sheet, from the homework, from anything. Just let me know. If not, I can just start from the beginning with polynomials and then just, pick and choose from there. So if you don't have any pressing questions, I will begin with polynomials, starting from the top. This is the first time I'm doing this, so I don't know how this will translate to your screen. I hope it looks good and you guys can understand this. Okay, I got a thumbs up. Long division. All right, let's go to long division. So we have synthetic and long division, right? So do you have a particular one from the 6 that we have here? So let's do long division. So I'll just start with the first one. Okay, so we have this division of polynomials. We have a numerator known as my what? This is my dividend, and this is my divisor. Now, how do we proceed with dividing this? We can either do two things. We can either do it through the method of long division, or because I have my divisor in the x minus a form, I can also perform synthetic division. I'll show both ways just to see how it's consistent, whether we do it one way or the other. It's just that synthetic division is a particular method of dividing polynomials whenever your divisor is of this form. And I would recommend doing the synthetic division if you ever see my divisor in this form, because it's just quicker and faster, and you're less prone to making mistakes. So if we were to perform long division, we would first have to say x minus 3, right? This is my divisor, and within this division symbol, I have my dividend. And then the question becomes, what do I multiply to this first term to give me this first term here? So what multiplies to x to give me 2x squared? It will be 2x, right? Because 2x times x gives me 2x squared. Great. So 2x times x is 2x squared. And then 2x times negative 3 is negative 6x. So make sure, once we find what this term is that multiplies x to 2x squared, I also have to multiply this term to this other term in the divisor. I get a negative 6x squared. And then I proceed by subtracting this polynomial with this polynomial. But whenever we subtract polynomials, we always have to consider the negative symbol, the negative sign, with the second polynomial. And so we distribute this negative sign, which means that we're going to negate or flip the sign of everything inside the polynomial. So now we have negative 2x squared plus 6x. And what happens is the 2x squared with the minus 2x squared cancels, and I'm left with negative 5x plus 6x is 1x. And I bring down the 3 and I get plus 3. So far, all we did was that first step. We found out what term multiplies to x to give me 2x squared. We found it. Now we multiply this out, and we have this new polynomial. Then we perform subtraction of two polynomials, and now we have this new polynomial. And we repeat the question again, right? We would say, what multiplies to x to give me x? Well, the only thing that multiplies to x to get itself is 1. So we add a 1. And then we say 1 times x is x. 1 times negative 3 is negative 3. But then I have to subtract. So I subtract. So when I subtract this, I have to distribute the negative sign to this term and to this term. So this becomes a negative x. This becomes a plus 3. And so when I combine these terms now, these cancel, and I'm left with 6 at the bottom. And since the degree of this term is smaller than the degree of this divisor, then we're done. Then this will be called my remainder. And this will be called my quotient. And this is still going to be my divisor. Now, what you need to remember is that division algorithm, right? If a polynomial divided by a polynomial results in the quotient plus the remainder over my divisor. So this is important to remember, that whenever you have a fraction of polynomials, like so, I want to figure out what's the result of this fraction. So I do, this is my p of x. This is my d of x, which represents the divisor. This is my quotient, so this is going to be my q of x. And this is going to be my remainder, which is my r of x. And now all I have to do is plug it in accordingly to this little algorithm that we have. So this here becomes q of x, which is 2x plus 1. And then plus 6 over, which is 6 represents my remainder. And my divisor is represented by x minus 3. So this is my final answer. So maybe use. So that's the answer that I get. I get my quotient, remainder over divisor. So that's how we perform long division on these two polynomials to figure out what's the quotient, remainder, and the expression. So that's long division. But because we have this nice particular form for my divisor, I can also use synthetic. And so this has the form, right? This needs the divisor. My d of x, my divisor, needs to be in the form x minus a, where a is the constant. In this case, my constant here is 3. So my a value here is 3. Now, how do we proceed with this method? We put 3 inside the box here. And then we put the coefficients of my dividend. What are the coefficients of my dividend? It's 2, -5, and 3. So these are coefficients of dividend. And then we draw one particular horizontal line. And the way this proceeds, I bring this first coefficient down. So this is the first step. I bring the 2 down. Great, I brought the 2 down. Now 3 times 2, I multiply this number with this number here. I get 6, and I put the 6 right there. And I repeat, I add -5 plus 6 is 1. Then I repeat, 3 times 1 is 3. And then I add 3 plus 3 is 6. Now this last number represents the remainder. These numbers here are the coefficients of quotients. My quotient is always 1 degree less than my dividend. The degree of my dividend was what? The degree of my dividend, well, my dividend has x squared, so the degree is 2. So the degree of my quotient will be 1 less. So the degree here would be 1, which means that the highest coefficient, the highest exponent in this polynomial is degree 1. So this goes with, my quotient is 2x plus 1. My remainder equals 6. And my divisor is still going to be the same, x minus 3. So again, my quotient is the same thing I got when I originally did it with long division. And my remainder is the same thing that I got if I did it with long division. Now I did it with synthetic division. So once I have these two things together, q of x, I got r of x, should make this equals, right? Then I can place these expressions like so, and I get the same answer. So this is how we did question number 1. This is number 1 from the review sheet. And we did it solving it in either long division polynomial long division, or synthetic division. So I hope that makes sense. So any questions about how to divide polynomials? Would you like to see one more, or would you want to continue with something else? Please let me know through the chat. I wish I could hear you guys, but I can't. So let's continue with which one? Which one, Elizabeth? Do you have one in mind? So let me just get out the way there and let you guys see that. Number 5 and 6. Okay. Perfectly fine. So number 5. So number 5 is 4x cubed plus 2x squared minus 2x minus 3 all over 2x plus 1. So again, this is my divisor. This is my dividend. Now, this divisor of mine does not have the form x minus a, so we can't perform, well, We can, but we're just going to be able to, we're only going to deal with the case when the divisor is x minus a to perform synthetic division. But this particularly does not have that form at the moment. So we have to perform long division. Long division always works. So whenever you have any doubts of dividing polynomials, long division always works. So now we have 2x plus 1, 4x cubed plus 2x squared minus 2x minus 3. So I don't know if it's going to take too long, but hopefully it does. It's not too long. Now, 2x, I asked myself, what multiplies to 2x to give me 4x cubed? And it's 2x squared. So 2x squared times 2x is 4x cubed. Then I do 2x squared times 1 is 2x squared. So then I subtract. And when I subtract, I need to make sure I change the signs within this polynomial, and I did. So now I can subtract. Now this guy goes away. This guy goes away, right? And I'm left with negative 2x minus 3. So it's not that bad. It's going to actually be pretty quick. Now 2x, what multiplies to 2x to give me negative 2x squared? Well, it's going to be negative 1. Negative 1 times 2x is negative 2x. Negative 1 times positive 1 is negative 1. And then I'm going to subtract them. Now this negative becomes positive. This negative now has to also switch the sign for the other term in the polynomial. Now when I combine them, negative 2x with positive 2x goes away. Negative 3 plus 1 is negative 2. And I'm done because I can't go any further. This is my remainder, r of x. This is my quotient, q of x. And this is going to be my d of x. So my final answer here will have p of x over d of x equals q of x, which happens to be 2x squared minus 1. That's q of x. D of r of x is negative 2, so I can put this negative sign here. Negative 2. And my divisor is 2x plus 1. So let me just write that here. So this is going to be q of x. This guy here is r of x. And this guy here is d of x. So that fits this mold here. And we're done. Final answer. Okay, so that's number 5. Hello, Xavier. How are you doing? Welcome. So that's how we did number 5. Okay, so are we good with this? Give me a thumbs up, thumbs down. Okay, good. Yes, yes. I got 2 yeses. Great. So maybe we can go on to some other topic. I know you still have number 6, but why don't you, Che, why don't you try number 6 on your own and see if you have any trouble with that? It's the same idea. Okay, Naji, we want rational functions. 3, 5, and 6. So rational functions. Five and 6. Okay, so we can start with 3. Yeah, Xavier, we are doing the review sheet. So, but if you have any other questions from any other things, just let me know. But for now, we're going to focus on the review sheet and see what we can do with that. So I'm going to erase this now. I will leave that up there. So we're going to be doing now rational functions. And we're going to do particularly number 3. So number 3 is r of x equals 3x squared plus 6 over x squared minus 2x minus 3. So this is our rational function. And what we want to find are all these items here, right? First, we want to find the x-intercepts. Now remember, the x-intercepts are the points where the graph crosses the x-axis. If you cross the x-axis, my y value will always be 0. In order for my y value to be 0, I need to set my rational function equal to 0. So I'm going to say that. So 3x squared plus 6 over x squared minus 2x minus 3. This must equal 0. It's the fraction, right? Fraction must equal 0. But the only way for the fraction to equal 0 is if my numerator were to equal 0. So then I really mean to say 3x squared plus 6 equals 0. Now, you may or may not see this, but this equation has no real solution to it. Let's say if we try to find what x is, right, you would probably subtract the 6 on both sides. And I get 3x squared equals negative 6, then divide by 3. And you get that x squared equals negative 2. And then to get x, what would you do? You would take the square root on both sides. But at least for this class, we're not going to have a negative underneath the square root because that would be an imaginary, or I should say, a complex number. So we're not dealing with complex numbers in this course. So there is no real solution to this. Since there's no real solution to this equation, and this equation comes from my numerator, meaning that my rational function can never equal 0, that means that I have no x-intercepts. So the x-intercepts are actually none. I have none because I can't solve this x value. I can't solve this using real numbers. I would have to use complex numbers, but we're not dealing with that. So in order to find x-intercepts, you set my rational function equal to 0, which means I set my numerator equal to 0 and solve. But in this case, I can't solve, so I have no x-intercepts. Now let's see if we have any y-intercepts. That's part B. Now, in order to find the y-intercept, that means that my graph must cross the y-axis. If my y-axis is crossed, or if my graph crosses the y-axis, at that point, we know that my x value has to equal 0, because that's what it means to be on the y-axis. Your x value is 0. So the opposite, things are alternating here. X-intercepts, y equals 0. Y-intercept, x equals 0. So we've seen this a lot, right? So in order to find what that y value is, I need to plug in 0 for x. So I plug in 0 here. And when I plug in 0, I get 0 squared plus 6 over 0 squared minus 2 times 0 minus 3. So all I did was I plugged in 0 into my function. That's what you have to do to figure out the y-intercept is. You have to plug in 0 into your function. And then you evaluate. So 3 times 0 squared, well, 0 squared is 0. 0 times 3 is 0. So I have this guy here becomes 0. And 0 plus 6 is 6. So what's left in the numerator is a 6. 0 squared is 0. Minus 2 times 0 is 0. 0 minus 0 is 0. So all of this guy here becomes 0. And I'm left with a minus 3. So 6 divided by negative 3 is negative 2. So what's my y-intercept? 0, comma, negative 2. So that's my y-intercept. I found it. All I had to do was plug in 0 for x and evaluate. So part C, I want to figure out what are the leading terms. For what? The numerator and the denominator. So we look at my numerator, which is up here. My numerator is this guy. And what's the leading term? Remember, rational functions are ratio of polynomials. And we know a lot about polynomials. We know how to figure out what the leading term is of a polynomial. And the leading term of a polynomial is the term associated with the highest exponent. So if we have this numerator here, we have a polynomial in the numerator. What's the leading term? Well, it's the term with the highest power, which is 2 here. So my leading term would have to be 3x squared. And same thing goes for the bottom. My denominator is down here. And my denominator is a polynomial. And what's the leading term of this polynomial? Well, it's the one with the highest power, which happens to be 2. So then this is, leading term would be x squared. So we found the leading terms of the numerator and denominator. And the reason why we do this is to find what? What do we use the leading terms of the rational functions to find? Well, it's to find the asymptote. And particularly, what kind of asymptote? It's the horizontal asymptote. So if I want to find my horizontal asymptote, I need to first look at the leading terms. And then I ask myself, are the degrees the same? Meaning, are the exponents the same? Are they different? Is one bigger than the other? Well, we realize here, the degrees are they're exactly the same. So the degrees are the same. So since the degrees are the same, we're left, remember we have 3 cases, right? Either the numerator can have a higher degree than the denominator, either the numerator and denominator have the same degree, or the numerator has a lesser degree than the denominator's degree. In this case, they're the same. So then how does that affect my horizontal asymptote? Well, my horizontal asymptote is the y value when you divide the leading coefficients. So the leading coefficients come from the leading term. The leading coefficient here is 3. The leading coefficient here is 1. So 3 divided by 1 is 3. So my horizontal asymptote is y equals 3. And we found that by finding the leading terms of the numerator and denominator and inferring what case I am in, right? What are the cases that I have? And then I found the horizontal asymptote by dividing the leading coefficients. Yes, so we'll talk about the domain and range. So this one is a little tricky about the domain and range, to tell you the truth. So last thing we have to figure out for the asymptotes are the vertical asymptotes. Now, the vertical asymptotes are found when you set the denominator equal to 0, because the vertical asymptotes are the lines that are vertical where my function is undefined. My function here is undefined if or whenever my denominator were to equal 0. So then when I have to find the vertical asymptote, I always have to set my denominator equal to 0. And the nice thing is that this denominator, which is a quadratic, can be factored into x minus 3, x plus 1 equals 0. So then you solve, right? And you get that x equals -1, and you get that x equals 3. So I actually have 2 vertical asymptotes. Now, Naji, for your question, the end behavior for rational functions are summed up with the horizontal asymptote. So the horizontal asymptote tells you the end behavior. It means that if you go far enough to the right and if you go far enough to the left, your graph is approaching the value 3. So the end behavior is really related, and we talk about the end behavior of rational functions. It's related to what are the asymptotes, particularly here. What happens at the ends? The y values go or tend or approach y equals 3. Now, are there any holes in this rational function? The only time there's a hole is if there's some factor in both the numerator and denominator that are canceled out. But none of them are canceled out because it's 3x squared plus 6. There's nothing. There's no factor here that cancels with this factor is here. So there are no holes. So part part E, there are no holes. And now probably the hardest one here is to find the domain and range. Now what I would do is I would graph this on my graphing calculator. And I would recommend highly to do so whenever you deal with the graphing of rational functions. So when I graph it, I'm going to show you guys what I get. So when I graph it on my graphing calculator, I put my numerator with parentheses, my denominator with parentheses, and I graph. So when I graph, I get this little kind of strange, it's kind of a strange graph here. So let's talk about it a little bit. And what I'm going to do additionally is I'm going to also graph the horizontal asymptote, and that's pretty simple. All I have to do is say y equals 3. So now I have my horizontal asymptote in red. Now, do you see how my graph crosses my horizontal asymptote at this point? But as you continue going on to the left, my graph approaches 3. So horizontal asymptotes in general, they normally aren't crossed or touched. But in the beginning, in the center of the graph, anything can really happen. But at the ends, near the ends, to the right or to the left, my graph is approaching 3. It doesn't become 3. Okay, so that's like the little exception to the rule of asymptotes. Now that we have all of this, let's just graph it. So let me just take this guy out here. I'm just going to erase this part because we already have it. So the first thing I want to draw are my asymptotes. So I have -1. I have 3. And I have 1, 2, 3. Horizontal. So maybe I should have drawn this with another color so you can see. So these are like my boundaries. I don't cross the vertical, especially the vertical lines, I don't touch them at all. Horizontal lines, horizontal asymptotes can be crossed, but in the middle, not at the ends. And so then, if we go back to our graph, you see there's no x-intercepts, so we don't have to cross the x-axis. There is a y-intercept at 0, 2. So at 0, 2, -2, I should say, this is my y-intercept. Right? And so then I'm going to copy this a little bit here. So this guy here is curving down like this. And now this guy here goes out here and gets close to y equals 3. And then this guy kind of like veers into the horizontal asymptote, but then it continues on this way. So there's my graph. There's the sketch of my graph. And now with this, I can find what my domain is and what my range is. Now, my domain is actually quite simple to find because they're the points that are all included except for the points where there's a vertical asymptote. So it's my x values all work except for the values that are my vertical asymptotes, which are -1 and 3. So I'm saying my domain will be -infinity to -1 union, -1 to 3 union, 3 to infinity. So that would be my domain. Now, what would be my range? So this is when it gets a little complicated, and you have to use your graphing calculator for this, because I want to figure out what's the maximum point here, what's the minimum point here, right? There's like a gap here with the y values. So I want to figure that out. So I would have to use my graphing calculator again, right? And this time I'm going to use second calc, and I'm going to go to maximum. And then I'm going to say, okay, I want to find, there's a maximum point there. There's a little hill here. So let me just put the left bound, and let me put the right bound. Put the right bound, and then make a guess. And I get that my y value, my x value is 0.37. My y value is negative 1.779. So this point here, the highest point is not negative 2, actually. It's, according to this, it's negative 1.779. I'm just gonna, that's my y value. Yeah. So that means that my y values go from negative infinity all the way to this particular point. So it's going to go from negative infinity all the way to negative 1.779. Of course, this is an approximation. And since we're attaining this point, this will be a closed bracket. Now the trickier one is to find what's the minimum point here. I know that I can't cross 3 here, but this kind of crosses through 3. So let's see if there's a way that we can find what's the smallest value here. So I'm going to go to minimum now. And then I'm going to see, okay, I'm going to see if I can skip this. Yeah. So this is a tricky one. I agree. So if you trace this a little bit, my y values go from 3, and then it dips to 2.5, 3, and then 2 actually, and then it starts to grow again. So I'm going to put it right before it dips and right before it goes back again. So it goes at 5.3. This is my left bound, and then I'm going to go back to 5.3. See how it dips a little bit? So let's see if there's a minimum here, and the minimum is 2.529. So this minimum point is negative 5.37, 2.53. I would write. And I'm attaining this guy. So my minimum y value here would be 2.53, comma, positive infinity. So I confess this is not that simple, particularly the range for this particular problem. But besides this, most of the rational functions that you will encounter, the range is going to be much simpler to find, and you can actually find it by the graph. The more important things that I want you to be able to do, particularly with the rational functions, are to find everything before this. Find the y-intercept, find the x-intercept, find the asymptotes, horizontal and vertical. If you can get those, no problem. Then finding the domain and range kind of follows from these things. Except for this guy. This guy, the range was a little tricky. It's a little tricky. But the domain was straightforward. It was straightforward. You find the vertical asymptotes, and you say, those are my x values. Everything else is good. So then I write it in internal notation, and I get the graph. And I'm definitely going to use my graphing calculator to help me sketch the graph of the rational function. Okay, so is this okay? Let me know. Like I said, the range is probably the more complicated part of this particular question. Not every question is like this, but this particular rational function is a little more work to deal with. Okay, we're good? Okay, good. Excellent. So what next? Do you guys still want to do more rational functions, or should we move on to something else? Because we still have 5 and 6 if you need it. So 5 looks like there's going to be a hole, and 6 looks like there's going to be a slant asymptote. Okay. So please let me know, guys, which particular question or anything that you would like to see after this. Can we do finding polynomial from graph? Yes, yes we can. So we have 4 of these guys. We have 4 polynomials that you can just. Can we go over graphing polynomials number 1? Okay, so number 1. So polynomial functions. Number 1. So number 1, we have it says write a polynomial function p of x. So I want a poly with degree 3. And yes, we'll go over exponents turning into logs after this. So we have a polynomial, degree 3, and what we have to pay close attention to is the graph that they give us. So the graph has very particular points, right? So if you look at the graph closely, we know that it crosses the y-axis at 2. This is important. So this is my y-intercept. My y-intercept is 0, 2. My x-intercepts are -1 and 1 and 2. So when I connect this is my graph. So I'm particularly interested in when does it cross my y-axis and when does it cross my x-axis. So it crosses my y-axis at 0, 2. It crosses my x-axis at 3 points. So this will be my x-intercept. My x-intercept is -1, 0. My x-intercept here is 1, 0. And my x-intercept here is 2, 0. So these are my x-intercepts. Great. So I found my x-intercepts. I found my y-intercepts. Now, how do I deal with this? Why does this help me? Well, again, my polynomial, I want a polynomial, right? And what I know about polynomials and the x-intercepts, or also known as, these are also known as zeros. These are the zeros. Why are they called zeros? Because when you plug in the x value into this polynomial, my y value is 0. That's why they're called the zeros. So we have to use what's called the factor theorem. The factor theorem states that if I have the zeros, I know the factors of p of x. So if I know that my 0 is at -1, this x equals -1 came from the factor x plus 1, right? Because you know when you factor the polynomial and you set it equal to 0, and then you solve for each of them individually, you would get this at the end. But now we are reversing our steps. We're given the 0. Now what's the factor that's associated with it? Well, if you add a 1 on both sides here, you get x plus 1. So this is one of my factors. Now I have the other 0, x equals +1. So my factor would be x minus 1. And then the last guy is x minus equals 2. So my factor will be x minus 2. So then why does this help me to find the polynomial? Well, because the factors of a polynomial, when you multiply them, give you the polynomial. That's what it means to be a factor. A factor are expressions or numbers that when you multiply together give you what you're looking for. So the factors of these guys, if I were to multiply them all together, if I multiply these all together, this will give me the polynomial, which makes my graph cross the x-axis at these particular points. My zeros, my x-intercepts. But I have to take care of one more thing. So these come from my x-intercepts. Using the factor theorem. But I have to just make sure of one more thing. There is a constant in front. There's a constant that I need to take care of. And this constant I can find by the y-intercept. So that's why I have to do these two things. After finding the x-intercepts, find the y-intercept. I use my x-intercepts. Great, I'm done with this. I used it by using the factor theorem. I'm done. Now I need to take care of my y-intercept. What does it mean to have the y-intercept being 0, 2? That means that if I plug in 0 for x, the result will have to be 2. So now I have to use y-intercept. What does the y-intercept mean? It means that if I plug in 0 for x, so p of 0, if I plug it in, I get 0 plus 1, 0 minus 1, 0 negative 2, and the result has to be my y value, which is 2. Then what happens? Well, 0 plus 1 is 1. 0 minus 1 is negative 1. 0 minus 2 is negative 2. So I have a times 1 times negative 1 times negative 2 equals 2. But then I can just multiply these things out. Negative 1 times negative 1 times negative 2 is positive 2a equals 2. So a equals 1. So there's really a 1 here. So then my answer would be this. This is in factored form. Factored form of polynomial p of x. And if I want the standard way of writing a polynomial, I'd have to multiply everything out, and I would have something of x to the third power. So I'm not going to do that here because I assume that you guys know how to do that because that's just algebra 1 really. So if you can get to this point, then you're in good shape. Then if I were to say, oh, give me it in standard form of a polynomial, you would have to do one extra algebraic step or several algebraic steps of multiplying everything out with each other. So you multiply this out together, this out together, and you get the polynomial. And you know what? Let me just do it real quick. So this will be p of x, right? X plus 1, x minus 1, x minus 2. Now the nice thing is here that this is x plus 1, x minus 1. If you multiply it out, this is a difference of perfect squares. So this is really x squared minus 1, x minus 2. And then you can FOIL. X squared times x is x cubed. X squared times negative 2 is negative 2x squared. Negative 1 times x is minus x. Negative 1 times negative 2 is positive 2. So this is my answer in standard polynomial form. This is standard polynomial form. So one is factored form, the other one is standard polynomial form. Okay? So that's how we use the graph of a polynomial to figure out what the actual function is. We have to first figure out the x-intercepts, use the factor theorem, find the factors. Then I put the factors together, and I need to find out what's the coefficient, the leading coefficient, and that comes from plugging in the y-intercept and doing some little bit of algebra. I find my a value, which is the constant value, plug it back in, and I have my factor form, and if I want the standard form, I have to multiply things out. And that's how you do it. Okay? So let me know if this makes sense. And the other ones are very much similar to this. You just have to do the same thing again. 2, 3, and 4 are exactly the same style, except that the other two have degree 4s in them. Okay? So if you have no comments or questions about this, we can talk about turning exponents into logs. Okay? So we're good with this. So if no questions about this, we'll move on to exponents. Exponential functions and logs. Okay, good. Good. All right, so I'll erase this now. I'm going to go on to, see, exponential. Yeah, let's just go on to, we'll go over compound interest. But first, we'll talk about how to go from exponential form to logarithmic form and vice versa. So this is number 4, logarithmic functions. So we have a little table here. We have the log form of it, and we have the exponential form. So we have to be extremely comfortable with going from one form to the other. So the first guy is log 8, 4 equals 2/3. So normally, we really deal with things in a more of an exponential way, right? This is just another way to write something in exponential form. It's called the logarithmic form. And what do we care about in the logarithmic form? We care about what's the base. My base here is that number underneath, subscript, which is 8. So I know that my base will be 8. So this is my base. Now, what do logs really represent? They represent exponents. What's my exponent that I have here? It's the output of my log. So 2/3 represents my exponent to my base 8. So I'm going to rewrite this as 2/3. So the equivalent way to writing this logarithmic form is to say 8 raised to the 2/3 gives me the input of log, which will be 4. Now the next guy is the exponential form. Sorry, this is 3. So now I have the exponential form, and I want to go back to the logarithmic form. So the logarithmic form is of the following style or form. You write the log, and the base, the subscript is the base. What's my base here? Well, it's 3. So this will be log base 3. But what is the input of my log? The input of my log is the output of my exponential function. Because remember, logarithmic and exponential functions are inverses of one another, which means that my domain range, my input and output are swapped among them. So if this is my output for an exponential function, then this will be my input for my logarithmic function. And then what's my exponent here? It's 2x. And remember, logs produce exponents. So this will be 2x. So going from logarithmic to exponential form to logarithmic form is extremely important and necessary to be able to do comfortably. You should be able to do this comfortably. Let's try the next one. we have e raised to the x plus 1 equals 0.5. So again, I have the exponential form, and I want to go back to the logarithmic form. Well, I recognize the immediate thing I have to recognize first is what's the base. And the base of this exponential form is e. So what's the log that I'm going to use associated with base e is natural log. So this could be written as natural log, ln. And again, what's ln? ln of what? It's ln of the output of the exponential function, which becomes my input. So this is 0.5. And the result of my logarithmic function is the exponent that I have here, which is x plus 1. So again, this is important now because now look, why do we go from here to here? Is that eventually we want to be able to solve exponential equations that have the variable as an exponent. How do we bring down the exponent? Well, we rewrite it using logarithmic form. And now let's do the last one really quick. So log of 3 equals 2x. So now I'm going to go from logarithmic form to exponential form. So the exponential form, I need to recognize what my base is. But whenever I see log just by itself, without any number here, I assume that this is a common log. It's the common log, and the common log has base 10. So I know that whenever I don't see any number, I know it's 10 automatically. So my base here is 10. What's my exponent? Well, it's exactly 2x. And the result is 3. So this is how I go from logarithmic form into exponential form to logarithmic form. And we have to be able to do this with ease so that when we deal with problems such as compound interest, it will be no problem to solve them because we have this basic algebraic step understood really well. Okay? So does that make sense? How to go from log to exponent, exponent to log? Can we do part 5, exponential log equations, question 1, part E? So part 5, question 1, part E. Oh, okay, so these equations, right? Okay, we'll do these and then we'll do compound interest, which is the one right the last page. Okay, so part 1, so exponential function. So exponential equations and logarithmic equations. So they're really intertwined. This thing idea here, this exponential and log equations are really intertwined. So what was suggested was part 1, question 1, part E. Okay, so let's do E. So now you see these equations that we're dealing with now are much more complex, or they look a little scarier than the ones that we normally deal with, right? Polynomials, that's what I've been telling you guys. Polynomial functions are nice because they're very easy structure. We know a lot about it. But the moment now we have e to the x with x squared, all this mumbo jumbo, it's like, what do we do? Well, don't fret. Don't be concerned too much about this. Whenever we have an equation, we always want to see what can we do? What can we do? What is it that we can do? Well, the only thing I can think of doing right now is to factor. Why can't I factor? Well, I have certain things that repeat itself in each of the terms, don't I? That's nice. I have e to the x in each of the terms. So what I would do, I would say, hey, wait, if they're all the same here, there's all common factors, I can factor out the common factor. So I get e to the x. And I can factor that guy out. Now I have the parentheses, and what's left inside? I have a quadratic. So I have an e to the x times a quadratic equals 0. So you see how everything we've been doing from the beginning is now coming back. Like I said, it's going to come back in waves. Why does it come back in waves? What am I referring to? I get this quadratic almost every time these type of functions and equations, right? I need to be able to do it with my eyes closed. I should be able to solve this without my eyes closed. There should be no issue because I know how to solve quadratic equations. If all else fails, use the quadratic formula. That will always save you in these cases. So now I have this product here equals 0. So if this product equals 0, that means that I can say e to the x equals 0, or I can say that x squared plus x minus 1 equals 0. So now I have two equations that I have to take care of. E to the x equals 0 and x squared plus x minus 1 equals 0. So we look at this first equation, e to the x equals 0. But you should be mindful of something here. E to the x is an exponential function. And we know that the exponential function e to the x, the range is 0 to infinity, not including 0. So this guy is impossible. This will never happen. But let's say you didn't know that. Maybe you took ln on both sides, right? If you take ln on both sides, this x value, this exponent, can be placed out in front because of the power rule that we have, right? So this becomes x times ln of e equals ln of 0. Well, ln of e is 1. So this answer is really x equals ln of 0. Now, what's ln of 0? Again, I can plug this in my calculator. Or I can figure it out, try to see what can I raise x to? What can I raise e to give me 0? But there is nothing. Nothing that I raise to e can give me 0. No value. So this actually, if you plug it in here, this is undefined. So there is no solution for this. So your calculator will give you an error. So actually, this side of the equation, this equation doesn't really help me in finding what x is. So then, since this doesn't give me anything, let's look at the other equation. Well, the other equation is just a quadratic. And we know how to solve quadratic equations. The nice thing is this is already set equal to 0 for me. Okay. The next thing I have to do is, can I factor this? Are there two numbers that when I multiply with -1 give me +1? Well, the only factors of -1 are 1 and -1, but when you add them, you don't get +1, you get 0. So you can't factor this. So if all else fails, like I said, you always have to use the quadratic formula. So then I get a equals 1, I get b equals 1, and I get c equals -1. Then quadratic formula. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So x equals, plug in, the a's, the b's, and the c's. So I get -1 plus or minus the square root of 1 squared minus 4 times 1 times -1 all over 2 times 1. And then I get -1 plus or minus the square root of 1 squared is 1, 1 times 4 times 1 times -1. This negative times negative is positive, so this really becomes 1 plus 4 over 2. And this becomes -1 plus or minus the square root of 5 over 2. So I get two solutions. I get x equals -1 plus square root of 5 over 2. And I get x equals -1 minus the square root of 5 over 2. And these are my two solutions. So whenever you have exponential equations, you always want to see if you can factor something first. If you can, do it. Then once you have the factors, then you set each of the factors equal to 0, then solve each equation accordingly. Nice thing is that we have a quadratic, and we know how to solve quadratic using the quadratic formula. We get the two solutions. We have two solutions here. The last thing you have to do, just to make sure, is to check by plugging these guys in to the original equation. If they do give me 0, which they probably will, these are my solutions, and I don't get anything else from here, e to the x. Okay. So good. We've covered a lot. We've covered rational, polynomial, logarithmic, exponential equations. So let me know if this is clear. If it is, then we will continue on with compound interest, which is like the creme de la creme of the problems that you'll see using logs and exponents. So are we good? Thumbs up, thumbs down? Yes. Okay, good. Okay, great. So let's do some compound interest then. So we can do the last one. We can do the last page. So this is number 1. So it says find the time. So see, these questions, they're asking you find the time. And time in these formulas was always an exponent. So it says find the time required for an investment of 5,000. So immediately I know, this is number 1. Immediately I know that my p-value is 5,000. That's my p-value. I want it to grow to 8,000, so that's my a value. That's the accumulated value that I want. And the interest rate is 7.5% per year, and it's compounded quarterly, which means that my n value is 4. And for half, yes. If I'm not mistaken, those two x values that we found are the solutions to the equation. You just have to check, and they should both work. They should both work. They should both be. So these two guys are the solutions. Because if I plug it back into the original equation, I get 0. Okay. So what I'm looking for here is t. I don't know what t is. So we're going to use my formula for compound interest, which is a equals p 1 plus r over n nt. I'm going to plug everything that I have inside. So I have 8,000 for A. I got P, 5,000. I got 1 plus. Now remember, whenever you have the percentage, you always want to convert it to a decimal. 0.075. That's my R. So it's going to be 0.075 divided by 4 raised to the 4t. So this is an exponential equation. The issue with this is that my variable is an exponent. But we know about logs. Logs take exponents and bring them down to the ground, which we want. So what I have to do first is isolate the expression with the variable. So the first thing I do is divide by 5,000. Now when I divide the 5,000 on the right side, the 5,000 cancels. And now these 3 zeros cancel here, and I get 8/5 equals 1 plus 0.075 over 4, parentheses 14. So what I will do now is make sure I do everything slowly, right? I'm going to evaluate what this guy is here, because I don't like having the 1 plus 0.0754 over 4. So I'm going to plug it in my calculator. So I got 1, right? I got 1 plus, and I put parentheses, 0.075 divided by 2. And I get 1.0375. So this guy here is 1.0375 raised to the 14. So I still have an exponential equation. But I want to bring down that t. So what I can do is use a log. I could take logs on both sides because these are two equal expressions. So if I take log on one side, it's the same thing as taking log on the other side. And here you can use either log base 10, log base e, or any other log base that you want. But since we have these common log and a natural log on the calculator for us, we should use one of these two. So if you like, let's use common base log. This will be log of 8 over 5 equals log of 1.0375 raised to the 4t, and all of that is inside of log. So all I did was I took log on both sides. Now the nice thing is, I'm just going to rewrite it here. So log of 8 over 5 equals log of 1.0375 raised to the 4t. So I rewrote it. And the nice thing is now, I can take this exponent and place it in front. So this will be 4t now is in front times log of 1.0375. So I use the power rule here. I use the power rule. So I use the power rule, and now look, I have the t. That t that I want, it's there. How do I get t by itself? Divide both sides. I need to divide both sides by 4 times log of 1.0375. And now the 4's cancel. The log cancels with this expression because they're the same. And I'm left with t on one side. And I got log of 8 over 5 divided by 4 log of 1.375. So all I need to do now is evaluate this. And the only way to really do that is using my calculator. And I will be very careful when I plug this into my calculator. So I'm going to plug in log of 8 over 5 divided by parentheses. So make sure I put the parentheses. 4 log of 1.0375. Close parentheses, press enter, and I get 3.1917. So I get t is 3.19174 dot 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 dot. So then you can say it would take approximately 3.2 years. So it would take approximately 3.2 years. If I were to round it, right? So that's how you solve this compound interest problem. Now the next problem is very similar, only that now instead of compounding it quarterly, we're going to compound it continuously. And instead of using this formula, we're going to use the a equals p times e to the rt. But the problem itself is exactly the same, meaning that we still want to figure out what that t value is. And we're going to use logs. And naturally, we're going to be using the natural log because my base here would be e. Okay, so that's how you solve a compound interest problem, trying to figure out what time is when it's compounded quarterly. If you do compound continuously, which is the next problem, you would have to use natural log. You could use logs too, but natural log would be the better choice. Okay. Yeah. So for the wholes, I want it to be x equals 1. That's when the whole occurs. It occurs at x equals 1, not x minus 1. But the x minus 1 tells you that x equals 1 is the point where the wholes occur. Okay? So I'll give you guys until 2:30. So we'll finish this live stream at 2:30. Let me know if you have any other questions that you want to do. Well, I'm glad, Claudia, you're working and listening. Good. Why did you divide by 2 instead of 4? Where did I divide by 2? Oh, Gabriel. Thank you. I made a little mistake. You're right. This should be 4. Uh-oh, so this is not right. So, okay. So let's rewind. Thank you, Gabriel. So this is divided by 4. So this is really 1.01875. So this number here will be 0.1875. This is really 1875. So this will be 1875. So all you have to do is now change these numbers instead. So if that's the case, then I'm going to change this to 0.1875 parentheses. So I get a completely different number now. I get 6.3252. This is 6.3. Thank you, Gabriel. See, you're paying attention, which is good. So I made a little mistake. To put the 2 instead of a 4 in my calculator, and that made a huge difference. You see that? You made one little mistake with the algebra can cause a completely different answer. Even if you do all the steps correctly, that little divided by 2 changed the whole outcome of the problem. So thank you, Gabe. So make sure, always check your work. And that's why it's good to always write it sequentially so that maybe you're able to spot, oh, look, what did I do? Did I do this correctly? Oh, I didn't. So then now, since I was able to catch that, or Gabriel was able to catch that error, all I had to do was change each of the numbers inside here. And I didn't have to really do much. Just change that number, and now I got the right answer. So yes, very good. Check your work. Be careful. Be detailed. Let's see. So rational function number 4. -2. So it's going to be positive 5. So yeah, there should be a whole at x equals 1. You're right. You're right. That's right. So for rational functions number 4, the whole is at x equals 1. Because the factor that's in common between the numerator and denominator is x plus 1. So, yes, the whole is at x equals. No, actually, because, okay, so let me just do that real quick. So this is in rational functions. Number 4. So r of x, my goodness, so r of x is x squared plus 4x minus 5 over x squared plus x minus 2, right? Right? So what you did was, let me see if there's anything in common with the factors, so then you factored it. So x plus 5, x minus 1 over x plus 2, x minus 1. Yeah, you're right. So then these cancel. So that means that x equals positive 1 is a whole. That's right. Yep. Good. So anything else, guys? More compound interest, more synthetic division, more polynomials. What else? What else? Graphing exponential equations. I don't think we've done that yet. You're down for exponential? Okay. So we can do one. Okay, so let's look at exponential functions, graphing exponential functions. Number 4. So number 4 looks like kind of a little complicated, but so whenever we do a problem like this, we always want to figure out what's the parent function first. So what's my parent function? Ten to the x. It's whatever that number is in the base, which is 10. So it's 10. Because 3 doesn't have an exponent to it. It doesn't have a variable exponent. 10 does. So 10 to the x is my parent function. And that should help me because I know what 10 to the x looks like. 10 to the x looks like an exponential growth function that crosses the y-axis at 1. That's 10 to the x. And what I'm going to be doing to 10 to the x is certain transformations. So what are those transformations? Well, I need to first look at my function that I'm dealing with. So I know 10 to the x is my parent function. And how do I go from 10 to the x to h of x, which is this guy? Well, this negative that's in front of 10 represents a reflection across. So 1. So I'm going to write this as 1. So this is 1 here. This is 1. I have a reflection across x-axis, yes. So the first thing I want to do is I'm going to flip this guy. First step, I flipped it. Second step, this plus 1 is within the x, right? I'm adding the 1 to the x. So that means, I should do another color. This means that my second point, my second transformation is a horizontal shift to the right, to the left. Pardon me. Horizontal shift to the left. By 1 unit. And now the last thing I have to take care of is this 3. But this 3, I'm adding it. I'm adding it. I'm adding this. So I can rewrite this as negative 10x plus 1 plus 3. It's the same thing. So I'm adding this. So this is going to be a vertical shift up by 3 units. So now I'm going to take, so first of all, I forgot to do the second thing. The second thing is I shifted it over to the left by 1. So now this guy is the second transformation. And the last transformation, I have to shift it up by 3. So I'm assuming that I might be crossing it somewhere like this. And now I need to figure out what's my asymptote. So what would be my asymptote? Remember, exponential functions do not have vertical asymptotes. They only have horizontal asymptotes. Now, originally, my parent function's asymptote was y equals 0. Then what did I do? I flipped it. My horizontal asymptote is still y equals 0. If I shift it horizontally, my y asymptote is still y equals 0. But when I shifted it up by 3, so actually this should be a lot. It should be a lot taller, I think. By 3. So this is 1, 2, 3. This is going to be my horizontal asymptote. So my horizontal asymptote should be y equals 3. Because the vertical shift affects the horizontal asymptote, not the horizontal shift. And then what's my domain and range? Well, my domain for any exponential function is always going to be negative infinity to infinity. And what's my range? Well, it's going to be all the y values up until the asymptote. It's going to go from negative infinity, because I'm going all the way down, all the way to 3. Not including 3, because this is asymptote. And just to make sure that this is a sketch, a good sketch of this, I would plot it, right? So I would say this is what? 3 minus 10. Now I'm going to put raised to the, just make sure I put parentheses, x plus 1, whoops, plus 7, plus 1, close parentheses, and then I'm going to graph. And when I graph, I have something that looks kind of like this. So then I just have to make sure that this guy here crosses it below. Something like that. And you see, if I plug in my asymptote to be 3, and if I graph it, it looks like it touches it, but we know that it's approaching it, not touching it. That's where the graphing calculator has its limitations, right, with the graphing. So that's how you do this problem here. All right, guys, so we did it. We did an hour and a half of a pretty decent old comprehensive review on what's going to be on the exam coming on Monday. Of course, there's a few more things to do here. We haven't touched every little nook and cranny. There's only so much you can do in an hour and a half, but Good. All right, guys, and I'll post the answers to this very shortly today on Blackboard, so you can do the problems and see how you do with the solutions, and hopefully I can upload this for those of you who were not actually on the stream as it was going live. Okay, so great, guys. So enjoy your weekend. Thanks for those 8 faithful of you who are here. I appreciate it. Hopefully this helped you with your studies, and best of luck on Monday. All right, guys? So I'll see you guys on Monday. Take care, guys. Peace.